rationalized. At this point in time, just let's assume the bending will not be seen in ground. As I said, it's not easy to visualize how the polarization will change. In the case of the antisymmetric stress, it's rather easy to visualize. You all have studied symmetry, and that's the reason I'm mentioning this to you right away and not waiting for some time later to do it. What is the big, nice symmetry element that carbon dioxide has? It's got many symmetry elements. There's one very unique symmetry element it has, a center of inversion. This molecule has a center of inversion. You remember what the point of this molecule is? The linear molecule D infinity H. So this has a center of inversion. And now, if you have a molecule with a center of inversion, there's a little rule that tells you, which is quite powerful really, which says that if a molecule has a center of inversion, then any vibration that is IR active will not be Raman active. And of course, using group theory and things that you have learned, and if you just push yourself a little harder, this can be very elegantly shown. Any molecule that has a center of inversion, that's the first thing that you have to understand. The criterion is we are looking at molecules with a center of inversion. If a molecule has a center of inversion, then any vibration that is infrared active will not be Raman active. So if you say that it is IR active, then Raman is out. And any vibration that is Raman active will not be infrared active. So if you recognize that rule, then it is very simple to figure out that why the bending should not be Raman active. Because we know bending is IR active, therefore it can't be Raman active. But please look at this rule carefully and internalize it the way I just said it. And the way I said it is, if a molecule has a center of inversion, point number one, if a vibration of this molecule is infrared active, then it is Raman inactive. The converse is not true, that's what I'm trying to harp on. Namely, if the vibration is not Raman IR active, then it doesn't mean that it will be Raman active. Converse is not true. If the vibration is IR active, then it will not be seen in Raman. If you don't see it in IR, then don't assume that it will be seen in Raman. The converse of that rule is not true. Because there are many situations where you will come across where a vibration will neither be Raman active, will neither be IR active. There are octahedral complexes where you will find vibrations of octahedral systems which are neither Raman active, neither IR active. And how do you even know what these guys can do? You got to use other techniques like optical absorption, electronic absorption spectroscopy to be able to see these vibrations. So the converse is not true. So if you ever tell me that Raman is inactive, therefore this vibration must be IR active, it's wrong. Raman is active, therefore it is IR inactive. Correct. IR active, therefore Raman inactive. Correct. But if it's inactive in one of these, then it doesn't mean that it has to be active in the other. It could be active, or maybe it will be inactive in both systems. And therefore the converse of the statement you must never mention. It's not true. And that's the way this is said, and this is called the rule of mutual exclusion. The rule of mutual exclusion is quite powerful really, because it tells you quite something about the nature of the molecule. Because let's assume that you have recorded a Raman spectrum and an infrared spectrum. And systematically you find that features that you see in one, you do not see in the other. And features that you see in this, you do not see in the other. What is it telling you straight away? It's straight away telling you that you are looking at a molecule with possibly a center of inversion. Supposing you had two molecules that you was given. If you remember your organic chemistry, this is still beam. And what still beam is this still beam or the trans still beam. Or if you want to use the ZE notation, this is Z still beam and the E still beam. Okay. And if I gave you this problem, I give you these two compounds and I ask you to figure out which is which using any experimental technique. What would be a nice thing to do? Record the Raman and the infrared spectrum for both of these. This molecule has a center of inversion. This molecule has no center of inversion. And therefore, what do you expect to see in this case? In this case, you will actually see that some of the vibrations will be both Raman active and IR active. And the moment you see any vibration that is both IR and Raman active, then you know the molecule does not have a center of symmetry. And immediately you know that that's what it is. Actually, the rule works quite well this way. Namely, that if you see both these, then you know that there is no center of symmetry in that molecule. But if you see one and you don't see the other one in the other spectrum, then don't jump to a conclusion that the molecule has a center of symmetry. Why? The feature might have been there. Your machine maybe didn't have the sensitivity to see it. Therefore, if you see a bunch of features in Raman, let us say, and you didn't see them in IR, then the statement you normally make is features that I see in one are not in the other. The molecule most likely has a center of symmetry. Regarding yourself against the possibility that there might be a transition in one of them, which looks like it is absent, but it's not really absent. It is there. It is just that my machine didn't have the sensitivity to be able to see it, and therefore I am led to the wrong conclusion the molecule has a center of symmetry. However, if you see common features in both of them, that's absolutely fine. You know that the molecule does not have a center of symmetry. Yeah. Pardon? No, you can't test. Yes, as always said, absence of evidence is not evidence for absence. Okay. So if you don't see something, be careful. It might be there. It's just that your machine does not have the sensitivity. That's why you are guarded. That's why I said, if you don't see this feature and it looks like the principle of mutual exclusion is operating, I see a bunch of features here and I don't see those bunch in the other spectrum, then it looks like the molecule has a center of symmetry. And the statement you should really be making is the molecule most likely has a center of symmetry.
Like we use in isotopes to be activated at light multiplication.
Yeah. No, see, this is an experimental problem. In the sense the intensity is very small and your machine does not have the sensitivity. Then of course what you should do is look for a better machine, better sensitivity and see if you can see it. But the other way around it's extremely powerful. In the sense that if you see common features in both, then you know for sure that the molecule does not have a center of symmetry, and therefore in this case what I will do is look for spectra where I see some matching spectra in both. And the ones that give me a feature in both Raman and IR clearly is belonging to a molecule that does not have a center of symmetry, and therefore it must be the system B. So the principle of mutual exclusion therefore is extremely powerful in the sense that you can go ahead and look for molecular structural information with IR. As I said earlier, rotational spectroscopy is very powerful in giving structural information because the accuracy with which you can get bond length, bond angle and dihedral angle information is extremely good with rotation. Vibration is not great, but it has got these features like principle of mutual exclusion and a few others, which actually helps you to be able to pin down what the structure might be. Though not as powerfully as rotation, but still quite very often, in many cases, you can get down to the structure using a bunch of rotational features. Yes, there's a question? Yeah.
What can we say about the range of the Raman? The range in which we can see.
Oh, can I see rotations? Can I see vibrations? Because one would be in the microwave, one would be in the. Yeah, we'll get to that. All I'm trying to do is to convince you that Raman spectroscopy has a pretty powerful enough application. And then we will get down to the question that is asking, where do I see? Can I see rotational spectra? Can I see vibration spectra? Can I see electronic spectra? But just to ensure that you don't have a speakers night to night, it can be seen right across. You can see microwave regions, you can see infrared regions, you can see UV visible regions, and we will see how that can be done. The point is, yes, you can see all of these. Supposing I want to see microwave region, just to quickly answer your question before I get to this. Suppose let's say, here's my B equal to 0, and these are all these lines. I have not drawn it correctly because the spacing must keep increasing. Let's say I use blue light, 450 nanometers. What will happen? I go up there, and then this should come down. Let's say it comes down to this. I'm not even worried about selection rules now, we'll cover that later. If it comes to this, what has my molecule actually done? It has gone from J0 to J1. So I see 450 nanometers, and I see 450 point some nanometers, that's the scattered photon. The difference in energy between these two photons will actually be this, and therefore, while my experiment is actually being done in the visible region, the difference in energy is actually being seen in the microwave region. If these two happen to be vibrational levels, then what will happen? The scattered photon will be 1000 wave numbers away. So it is still an experiment in the visible region, but the difference in energy is going to be in the infrared region. And therefore you will see that this experiment actually works for any region that you really want. You can do rotational spectroscopy using Raman and using an incident light in the visible. You can do vibrational spectroscopy, which should really be occurring in the infrared region. And how am I doing the experiment? I'm actually doing the experiment using blue light or red light or whatever, visible light. So I'm using light of frequency something like 400 nanometers or wavelength like 400 nanometers or 450 nanometers. But the difference in energy between the scattered photon and incident photon, that could lie in the microwave, that could lie in the infrared, or it could lie in any of the other regions that I'm really interested in. So the range of the Raman spectroscopy is really quite wide. Yeah.
Is there any factor which will determine that after going to the virtual state it will stay or it's all random? Like after going to the virtual state it will come down to any level or there is some probability difference?
There's again a probability because now I think you are sort of pushing me far too ahead of what I plan to say. You said this, right? Psi prime, mu psi, prime, to find out the intensity of absorptions. Now, what do you think should be here? And then you evaluate, and then you see what happens. So it's not just random. There is a lot of method in the madness that goes on over here. Okay. Just to give you some feel for, why Raman spectroscopy. Today, Raman spectroscopy is absolutely useful. It's probably one of the most sought after techniques. Biologists will actually swear by it. They will swear by Raman spectroscopy. Well, chemists too. But biologists will swear by it. Why is it? Actually, when Raman discovered it, he used a mercury lamp and then showed it in the case of alcohol. He's capturing it, and then found that. And then, of course, as I said the other day, the rest is history. He published that on 28th or he reported this on February 28th, and that's what we celebrate that as science. And there's also many other stories that I really can't believe. Apparently, Raman was so sure that he would get the Nobel Prize that year. It is said he even booked his air ticket long before the announcement of the Nobel Prize was made. I don't know. Raman is around to confirm that. So anyway, that was what it was. There's another nice story. Of course, there's one nice story said about Raman when he sat there in the Swedish Academy to get the Nobel Prize. He said, every other Nobel laureate who sat there had the country's flag behind them. We didn't have it at that time. He said, that's what hurt me a lot. I was not sitting in the banner of the Indian flag, but on the Union flag. That's what he said. So that's another incident was told of what Raman felt at the Nobel ceremony. And of course, after the ceremony, there was also this a banquet, and Raman was asked to, glass of whiskey or alcohol was offered to him, and being a teetotaler, he said, no, I will not. And they kept insisting. He said, no, you have seen the Raman effect on alcohol. You certainly don't want to see the alcohol effect on Raman. So, these are some very nice anecdotes that are told. So he apparently he had a sense of humor and he got away with what he wanted. Because people's parents, it's very, it's not very social to refuse a drink in a party. He said, no, I'm a teetotaler, I will not have it. And if you see pictures of Raman, you can see extremely conservative person and turban and all that. And of course, he got away with this by making this very human statement. And we really don't want to see the effects of that for Raman actually discovered this technique using a mercury lamp. A mercury lamp is just a little glass envelope with some mercury vapor in it, you strike a discharge, and you see the emission from mercury, and you use that as the excitation source to do all these scattering experiments. Very weak, mind you. And the Raman process is also very weak. The scattering process is not an extremely strong process. The absorption process are much better than this. Therefore, the Raman process is basically, that's one of the reasons why it was so difficult to be able to actually see this process. And that's to the credit of Raman and the relentless pursuit in what he wanted to see, that he got his way. And soon after Raman effect was discovered, people realized there was some very huge contribution in fundamental spectroscopy. That's the reason why he got the Nobel Prize. Few years, people looked at various molecules, and after some time, the interest seemed to be just waning because we were not getting anywhere. You're not getting anywhere because it is so weak, and how much, and what sort of characterizations can you make with it? Not all a lot. And therefore, the interest in Raman spectroscopy at one time was actually dying off. Luckily for Raman, 1961, Ted Payman makes the first laser, the ruby laser. And ruby laser, mind you, and all lasers that followed thereafter were extremely powerful light sources. The mercury lamp, I don't know, no pun intended, couldn't even hold a candle to this laser. It was extremely powerful. And once you had the laser out there, you could now do these Raman experiments with the laser. So you had the very powerful sources, and therefore your scattered photons were quite intense. You could actually measure them. And the moment the lasers came into play, Raman spectroscopy became again extremely very important because now you could do characterization quite comfortably with the very powerful laser sources. And that's essentially what is believed, that Raman spectroscopy actually got a new lease of life when the lasers were discovered. Had the lasers not been discovered, we probably would have one chapter less in the 201 course. I don't think we would even bother about teaching you about Raman spectroscopy if it was not for the fact that it is so extensively used. When I'm done with Raman, maybe the last class, or maybe half a class on the last day of the Raman thing, I will tell you things that are not in random and which will not be for the exam, but we will talk about higher order Raman processes. Raman processes which are actually occurring because of the intensity of the laser sources, which could not have been seen by Raman, because the sources were too weak to provide you this higher order processes. There are so many higher order processes you will see in Raman, with all very fancy names like cars and porcelains and so on. They're all the names for the techniques. We will see that. But as of now, what we are looking at is the fundamental Raman process which Raman discovered. Shine light, molecule hits this photon, scatters off another photon, and if you look at these two photons, the incident and the scattered photon, take the difference, and that difference is telling you something about the energy state in which the molecule is left. If this intensity is strong, the scattering intensity is strong. This intensity is strong in the case of the laser, and that's the reason why today, if you look at it, all Raman experiments are basically done using lasers. Okay? We have a Raman experiment from McCash has it. Go and ask him. Of course, you will see it in the 211 lab course. We do take you to a little trip to NMR and Raman, and you will see how it is recorded, and you will find that it's basically going to be using a laser for all these experiments. Again, you will see that there are lasers and lasers. You got lasers in the 400 nanometer region, you got lasers at 200 nanometers, 5, 6, 800, so on. You have a whole variety of lasers that one could use. Is there any constraint on which laser I must use? No, because we just said the scattering really doesn't depend on which wavelength you have to use. You can use any wavelength. It is not an absorption emission process. It's a scattering process. And therefore, I can really use any wavelength. All I have to do is to look at the frequencies of the incident photon and the scattered photon. And that difference is always going to be a constant for a given transition from which I get information about the state in which I am dealing my molecule. But there is a huge advantage to be gained where using short wavelength lasers or long wavelength lasers. What do you think would be a good thing to do? If you are given a choice between a 400 nanometer laser and let us say 700 nanometer laser, which one would you take? Short. Why? Yeah, scattering is much better because it is 1 over lambda by 4, and therefore you will find that it's always nice, it at least seems very smart, that you use a short wavelength laser. very quickly you will find it's not smart to use a short wavelength laser. And if you really look at all these experiments, they're really done with long wavelength lasers. Why? When you use a short wavelength laser, like a 400 nanometer laser, what happens? The molecule can scatter. But then see, you don't dictate to the molecules what they should do. They just do what they want to do and you sit down and try and rationalize what they're doing. So here's the molecule. You shine 400 nanometers saying that, okay, I will do a scattering experiment. Yeah, you want to do a scattering experiment, it will happen. But if the molecule has an absorption at 400, it will absorb. And when it absorbs, what does it do? It goes up to the excited state and then comes down giving you light again, emission. And you started doing fluorescence. Okay. Fluorescence experiment. So the molecule is not going to sit quiet and do just a scattering because you wanted it to do that. No, the molecule will do scattering. The molecule will also do fluorescence. It will absorb and emit. And you have the strong fluorescence that you will be getting. And in this strong fluorescence, you got to see this weak Raman. And that's your problem. So if you use short wavelength light, yes, your scattering efficiency is really good. Therefore, you think it's a smart thing to do. But the molecule has other designs. It will start doing a fluorescence experiment that you don't want to do. And this fluorescence generally is extremely strong for many molecules. And if you have a very strong fluorescence, you are really sunk. You will not be able to see the Raman lens. So what do? You take a wavelength in which the molecule does not absorb and therefore cannot give you fluorescence. And all you will now have, so you're going to sort of trick the molecules. You give them frequencies or wavelengths of light that are inappropriate for an absorption emission process. Now, most organic molecules you will see will absorb at 3, 4, 500 nanometers. Give them 750 nanometers. There's hardly any state that there is for absorption in many molecules. Some molecules do have states even at that, but most will not have an absorption at that point. So if they don't have an absorption at that point, what's the only thing you're going to be seeing? Raman. And therefore you see Raman without contamination from the absorption emission process. So what have you done? You have actually lowered the efficiency of your scattering process, but you have discriminated extremely strongly against the fluorescence. Smartly use 400 for scattering, but very bad, simply because you have an emission going on, a fluorescence experiment going on, much against your own desires. So what you have to do therefore is to use a wavelength that is not going to be appropriate for an absorption process. So use 700 nanometers and you will find you have lost out on scattering, but you have gained on this differential process. You have completely suppressed fluorescence, and all you're going to be seeing is only the Raman process. And of course, whatever you have lost out in terms of the scattering efficiency, you can always make up for it by just jacking up the laser intensity, which of course you can do. And therefore, you see, it's a very smart thing really to be looking at wavelengths that are quite long in a Raman experiment. So if you go and ask them what wavelengths you are using, they'll always give you 632. 632 is the wavelength for the helium neon laser, or maybe a 700 plus, which is a diode laser, and so on. People use that. Very rarely you see people using 400 nanometers or 450 or 300 or 500 nanometers light for a Raman experiment. Because if you do that, you're basically killing yourself with a strong emission that you will see. And it's very hard to discriminate that light from a Raman process. That's the reason why you use really long wavelength. But so far as the whole technique is concerned, to give you the basic processes that go on in the technique, I said it's a polarizability driven experiment. It is not a dipole moment driven experiment, it's a polarizability driven experiment. And the molecule must have a changing, time varying polarizability as a function of the process you're seeing. So if you're seeing a vibrational system or a vibrational pattern that you want to recognize in the molecule must have a changing polarizability with respect to vibration. And we saw a few examples of carbon monoxide, carbon dioxide, we saw it with hydrogen, nitrogen, and so on. None of which will give you an infrared absorption, but all of which will give you Raman scattering experiments that that you could actually observe. Now that we have seen all this, now let's get into the specifics. And what do I mean by specifics? We're going to see how I can use Raman to look at rotational spectroscopy. We'll see how we can use Raman to do vibration spectroscopy. We will stop the discussion at that point. We go to electronic spectroscopy and we will visit Raman again to see how we can do Raman for an electronic spectroscopy experiment. What was the selection rule in an absorption process? We saw that delta J must be equal to plus minus 1, and where was this plus minus 1 coming from? When you evaluate the transition probability interval, throwing in the appropriate wave functions, and package the wave function to dipole movement operator, evaluate the integral, you will find that every time the upper state and the lower state differ by 1 quanta of J, the integral is non-zero. If they do not differ by 1